recording. This is slightly different than how I have taught it in the past. We'll see how it goes. Flip the page. Find me this cool little graph dealy right here. Okay, so we're going to talk this through a little bit. What is going on with these points on this graph? Tell me what you see. It's like one of those ink blots you see when you go to a psychiatrist's office. What do you see? A triangle. If you follow the alphabet, it's a triangle. As Rebecca has pointed out, there is no letter E. Okay, so we're noticing a triangle here, yes? So then what I'd like you to do, if it bothers you to draw, like to freehand some straight lines, you know I always have a set of rulers. If you'd like one, come get one. They're up here at the front. But if you can freehand draw a straight line without screwing it up too badly, then let's do this. So we're going to draw, actually, and how many triangles are there actually here? You can make a lot, I think. Okay, so let's try and make a lot. So the first triangle is we're going to draw a line from A to D. And then we're going to draw a line from A to H. And then we're going to draw the last line from D to H. That didn't really go at all, so I'm going to thicken that guy up a little bit. 2 C's. That didn't really work at all either. I'm going to thicken that guy up again. There. Haha! Love it. So, and then I'm going to, let's just draw this one again. Make it a little thicker so we can really see what's going on here. Okay, so we've got one triangle here. This main triangle, I don't know if you've ever named shapes before, but the way these shapes get named, the one that we've just now drawn, is we say that this thing is a triangle by drawing the symbol for a triangle, and then we give the letters for each of the vertices, and a vertice is just a corner. We've seen this, have we experienced this kind of language before? Yeah. So then what we've just drawn here is triangle ADH. What kind of triangle is this? It is a right triangle. How do you know that this is a right triangle? One of them is a right corner, which, as Nika has just said, is a 90-degree angle. Which one of these is the 90? The bottom right. So we say, so let's just put some language in here for a bit of a review. This is a right triangle. Angle, and how you write this, so that is an angle. That is not a greater than sign. That is an angle. We say angle H is equal to 90 degrees. That is the notation for how we write all that down. Is this new notation? Have we seen this before? Just kind of something you just did. Okay, well, then let's get you, So I'm hoping, it's not like it's super complicated. I just want to make sure you understand the notation. So there we've got a triangle ADH. It's a right triangle. Angle H is the 90. What other triangles can we make here? Not actually so many. We can actually make a fair number of them. Let's reduce that. How many right triangles can I make here out of the vertices that we've been given? Carolyn has already given us one. I heard back there. Say it again, Carolyn. A, B, and F. So we're going to draw a vertical line. I'm going to draw it in blue for those of you who are using the same colors I am. There's A, B, F. Okay. And then my right angle on that one is angle F. Okay, cool. What's my next one? GCH. Ooh, while that is true, it would totally defeat what I'm trying to show you. There's only going to be 3 that we're going to focus on here. Okay. And there's a reason for that. So we're going to draw, though, this CG is the last line we're going to draw here. I'm going to draw it in pink for those of you who care about using the same colors I do. There we go. So we've got 3 triangles here now. We've got ADH, we've got ACG, and we've got ABF. These are the 3 we want to focus on. Does anyone know what is special about these three triangles? They're all right angle triangles. What else is true? So let's draw in those right angles here. So this is the symbol that we use to denote that an angle rather is 90 degrees. We put a little square in the bottom corner. That's a 90, that's a 90. This is a 90. What else can you tell me about these three triangles? They're all connected at A. We cool with that? So we have this triangle, we've got this little guy here, we've got this big one here. An angle that they all share is this one here. And so I'm going to denote that by drawing three little curvy lines here to denote that my blue triangle, my pink triangle, and my black triangle all are connected here at A. So they all share that angle. So then what else is going to be true about these triangles? Okay, so let's, here, one second, all right. Yes, there we go. Okay, I want to make sure I have the right notation here. So then what you're suggesting here is that, so yeah, because they share that angle, the slope of the hypotenuse is the same for all of them. That's good. What else do we know is true? If this angle is shared on all of them and this angle is the same on all of them, Presley?
The angle of BC and D will all be the same.
The angle BC and D must also then all be the same. Okay? So we're going to denote that. I'm going to use a light blue, little curvy dealy arc. That guy, and that guy are all going to be the same. This is going to be useful to us here. So I'm going to say that angle B is going to be equal to angle C, which is going to be equal to angle D. That is useful information to us for reasons that are going to become evident here in a sec. So we've got those three are all equal. We've got, I'll add this one down here too. Angle A is shared. And then the last one, I'm missing dark green for some reason. So we'll clash a little bit and go to orange. Angle F equals angle G, which is equal to angle H, and all of those are equal to 90 degrees. There is something special that we can say about these triangles if all of the angles are equal. They are not equilateral. Equilateral means all of the angles, sorry, I said that wrong. It's an equilateral triangle if all of the angles within a single triangle are equal to each other. But if all of the, so how the language we use here is we say all of the corresponding angles are equal in these three different triangles. So like they all share A, angle B, angle C, and angle D are all the same, angle F, angle G, and angle H are all the same with each other. And we've got three triangles of different sizes here. So we can't say that these triangles are equal to each other, but what we can say is this. We can say, and I'm just going to do, what color am I going to use here? I'll use the three different colors. We'll say triangle ABF is this little symbol, single little squiggle, with ACG, give another little squiggle, triangle ADH. And what that little squiggle means is that these triangles are all similar to each other. So these triangles are all similar.
Why did you put a squiggle on the last one?
Sure, let's put like here.
No, like on the ADH.
There's a, this one is similar to this one, which is similar to this one. is how you read that how you read that sentence. And that symbol there means these triangles are all similar. For triangles to be similar to each other, they're allowed to be different sizes, but what you have to be able to do is expand them into each other. Like, if we multiply all of these sides here, let's say so this side length here is 4, this side length here is 5, 6, 7, 8, 9, 10, 11, 12. If I triple all of the side lengths here, I'm going to get this next bigger triangle. 13, 14, 15, 16, 17, 18, 19, 20. If I multiply all of the side lengths here by 5, I'm going to get this bigger triangle. So if you can, we talk about scaling things up. Have you guys looked at scaling things in middle school math?
Not really.
Okay. But you understand that idea of multiplying all of the dimensions by the same number to get a larger object?
Yeah.
So we call that scaling. So we're going to scale these guys up to give us a larger triangle. If you can do that, and we know we can because all of the angles, all the corresponding angles are equal to each other, we say that these things are similar. Now, trigonometry, the field, let's call it a field. The field of trigonometry in mathematics uses relationships that we can draw out of these similar triangles. So what I want to look at here is a couple ratios. So down here, we're going to slide this up. I'm going to blow this up a little bit here. I apologize if things get a little not out of hand. Out of hand is the wrong word, but hard to read because they're so small. We're going to draw 3 lines down here, breaking the bottom of my page up into 3 sections. We're going to label this one ratio number 1. We're going to label this guy here ratio number 2, and we're going to look at here ratio number 3. We remember what ratios are, yes? Not really. Some of us say yes, some of us say not really. What is a ratio? Someone who remembers. Amina, you were nodding aggressively. How would you explain what a ratio is?
It's almost like a fraction, only not really. It basically says that if one thing gets bigger, then the other thing gets bigger at the same scale. So it would be like the ratio of 1 to 2.
Okay.
So like if you...
Which we could write as a fraction, which is why I think you're saying that they're like fractions but not.
Yeah.
Okay. So yeah, they are similar to fractions. They get notated like fractions, which I think is where some of the confusion comes between what a fraction is and what a ratio is, because we notate them the same way. When you think of a fraction as a fraction, you're looking at a part of something. So like if something is half filled, the fraction we would use to represent that is 1 over 2. But we can also use that same notation to look at things that are, like if you have one object that's twice the size of another object, we say the ratio of these 2 objects is 1 to 2. Sometimes we use a colon in there to represent that notation. Sometimes we actually write it as a fraction. So we have the same notation to represent 2 different things. This happens all the time in mathematics where we use the same notation and then all of a sudden just kind of magically we're using them in the same way without really explaining why we can do that. And this is another one of those scenarios where the notation for ratio is the same as the notation for looking at fractions of things, and we're going to treat them as though they are both division, which is what they are, and which is why they're kind of related to each other, even though the ideas behind them are different. So the first ratio that we're going to look at here is not the ratio between different shapes, but between different sides within the same shape here. So we're going to look at the ratios in these 3 different triangles of the following sides here. We want to look at side BF, which is how I'm labeling that little guy down there. And I want to look at the ratio of B to F to the side A to F. And so that's how we typically write a ratio. Instead of writing it like that, I'm going to now change the notation. I want to use the fraction notation for a ratio. I want this one, BF over AF. I'm going to zoom this in a little bit here to make it easier to see. And I'll be zooming in and out. Hopefully it doesn't screw you guys up too badly. What is that ratio? Is that true? How long? So this is, BF here is the side BF. Right. AF is the side that connects A and F to each other. How long is BF? Yes. So we say the ratio of those two side lengths is 3 over 4. Because this guy here, BF, is 3 long, and AF is 4 long.
Okay. No,
The angle is going to play in here in a sec.
Okay, that makes sense. I was looking at it.
And so we say that the ratio of those two side lengths is 3 over 4. Let's look at, we're going to do the same ratios in the two larger triangles here. So side BF relates to what side in the pink triangle? CG. This guy here, right? So we've got BF over AF is 3 over 4. So we're going to look here now at CG over AG is what?
Should we not write this in the ratio 2?
No, this is also ratio 1. Believe it or not. CG over AG, what are those values there for the side lengths there? 9 over 12, which Rebecca just whispered reduces to 3 over 4. So what is the corresponding ratio then in the in the biggest triangle? Let's look at DH over AH. That's, what is it before we reduce it? (16 over 20). And I can, is it 16 over 20? I'm pretty sure it's 15 over 20. It better be 15 over 20. Because both of those 15 and 20 are divisible by 5, giving us what ratio? 3 over 4. This is really interesting. So it doesn't actually matter which triangle we're looking at here. The ratios of those two side lengths are the same in all three of those triangles. That's interesting. That's a neat little relationship. So in general, for a right triangle, we're gonna give a name to this ratio. Okay? We're gonna say that, well, first of all, yeah, we'll say that starting here at angle A, if you take this side and this side as they relate to angle A, it doesn't matter how big the triangle gets, similar triangles are gonna have the same ratio. Now, if you had to give this side here, this tall side here, a name from this angle, what might you call that side?
Kevin?
Not calling it Kevin.
What do we use besides BF and AF and not CA?
Sorry?
Why do we use BF and AF and not CA for AG?
We'll get there, because I'm focusing on a particular set of sides right now. So if I told you, okay, we're going to start here at angle A, and we're going to this side, how does this positionally, I'm going to see if I can draw this word out of you. Thank you. Have you seen this stuff before? Ah, so you know all the language. You know.
I remember some of it.
Okay. So what we're going to say here, thank you, Amanat, this side here is across the triangle from this angle. So the language we're going to use here is this side is opposite the angle that we're referencing. Well, for two things to be opposite each other, there's a couple versions of that word opposite. If things are opposite from each other, they are different in every, like perfectly different in every conceivable way. Okay? Another word for opposite is if we say things are opposite each other, they are directly across from each other. So positionally, we would say Rebecca and Amanat are on opposite sides of the class because they are exactly in the same position but directly opposed to each other. In my seating plan, they are exactly opposite. So you are opposite Angel, Presley is opposite Kyla. Okay, so again, we're using, in the symmetry that is this classroom, you guys are opposite from each other. And almost all of you have opposites. Things get weird in the back corner there because I have a different number. Actually, I have the same amount of desks on each side, but they're positioned a little bit differently. But at least the front row works. There are opposites in the front row. And so we're going to use that version of opposite. So we say, okay, this side here is opposite this corner here. Okay, so what we're going to do is we're going to call this side the opposite side as it relates to this angle here.
It's just on the other side?
Because it's just across from it, yeah.
Oh, I thought it had something to do with the way it tilted in a certain
No, no. See, and the danger here for those of you who overthink things, the danger here is that this stuff is really easy to overthink. Don't do that.
Okay.
As much as you can prevent it, don't do it. So this side is opposite that angle. And now we've got side A. The other side to be looked at is this bottom side here. How does this side relate to this angle? It's beside it. Is there a fancy word that anyone knows here that means to be beside something? It's not parallel. It's not going to be parallel. Do not flip ahead. Don't flip it. Adjacent, yes, that is the word that we're going to use here. Hands up if you've heard this word adjacent before. Okay. To be adjacent to something literally means you are beside something. So we're going to say that side AF is adjacent to, and adjacent is spelled ADJACENT. We're not going to spell that out every time. I'm going to abbreviate it as ADJ. So we are going to call ratio 1 the sides that are the ratio of the opposite side, which I'm just going to say OPP, divided by ADJ, the adjacent side. Sorry? AB is, but there's something special about that particular adjacent side. What is special about side AB? It's sloped, and AB is opposite from which angle? AF. No, so angle? Angle F. So the side that is opposite the 90 has its own special name. We never talk about it being adjacent because it has its own designation. What is the designation for the side that's across from the right 90 in a right triangle? Starts with an H. The hypnotus. We don't call it that. That is not how we say that word. It's the hypotenuse. Hypotenuse. It sounds really pretentious, but that's the word that we use. That's the name that it's given. Hypotenuse. And I'll zoom that in so it's easy to read. This side is called the hypotenuse, Hypotenuse. Hypotenuse. And the hypotenuse is always across from the 90. That guy there is the hypotenuse. So that's why, Carolyn, we say that AF is adjacent because AB has its own name. It's already the hypotenuse. It doesn't need to be named as it sits next to someone else because it has its own name. So for example, let's say I didn't know Danny's name. I would say, hey, you, the girl that sits beside Presley. Right? And I would know Danny as she relates to someone else that I know. So let's say, it's 6 weeks into class and I see this person in the hall. I still haven't learned her name and I say, hey, you're the girl that sits beside Presley, and that's how I refer to her for the rest of forever. That's what we're doing here with side AF. I happen to know Presley's name, and so yes, I could say, yes, you, the girl who sits across the aisle from Kyla, but because I already know Presley's name, Presley has a designation. Presley is the hypotenuse. We use the name designated to the individual as opposed to their position relative to something else in the triangle. Does that make sense? Okay.
Wait, I was too focused on the word hypotenuse.
Oh, that's sad.
So what does it mean? Because you said
It's the side across from the 90. It also happens to always be,
the slope thing, the angle.
it depends how I spin this. Hold on. Don't say those words. Don't say those letters in that order. Nope, and don't whine at me. We'll get there. What is interesting about the hypotenuse in every right triangle? Does anybody know?
Is it always at an angle?
No, because I can spin this and make this all sorts of weird. It could be the flat side.
Oh.
In addition to always being opposite to the right angle, it is also always the longest side in a right triangle.
No way.
Always.
No way. Shocking.
Always the longest side. in a right angle triangle? Okay, so this guy is always the longest side in a right triangle. And I know I'm writing on graph paper, and I know it makes it harder to read, but that's okay. We'll deal. Yes, Carolyn?
Like it's the opposite, like why is it the opposite of the angle A and not the opposite of angle B, for example?
What do you mean? Why am I choosing angle A? Because I am. It's arbitrary. You're right. It is totally arbitrary. Could I have started with angle B? Yes. My ratios would have been a little different, but that's okay. I could have started with angle B. I have just, for the sake of this example, I have just chosen to start with A, which designates this side opposite and this side adjacent. You bring up a good point. If I had started with B, which side would be opposite? AF would be opposite, and BF would be adjacent. BA would still be the hypotenuse. Okay? So the important thing here is, and Carolyn brings up a really good point, opposite sides that are what we call opposite and adjacent are always relative to the angle that we've chosen to start from. It feels to you like it's totally arbitrary. Could we have picked B? Yeah, I didn't. I picked A for reasons that I'm just going to keep to myself. But it is totally arbitrary. Okay? So this is, and I'm going to make a note here. These ratios are all relative to angle A. And I think it's good, Carolyn, that you asked that question because I would have totally forgotten to say that earlier. All relative to angle A. You can do this all using angle B, C, and D if you'd wanted to instead, but I chose A. Okay, so we've got a first ratio. We say the ratio is, we call this the opposite and adjacent. It happens to be the same in each one of these triangles. That's neat. Let's do the same thing for ratio 2. Now, instead of looking at BF and AF, we're going to look at sides AF and AB. So let's look at side AF over AB. How long? What is that ratio? AF is 4. What's AB? Is it? I don't know, is it? What is it?
4 times 4 squared is 16, and 3 squared is 9, and 16 is 9.
Oh, you're using secret hidden knowledge. I like it. So using secret hidden knowledge that you were all supposed to learn in grade 8, it's 5. Using secret hidden knowledge that you're supposed to learn in grade 8, that I will teach you about later, that side is 5 long. AB is 5. If you don't already know how AB is 5, don't worry, we'll get there. But we're going to, this is,
Are we still looking at the first triangle?
yes, we're still using AF and AB.
Okay.
This side here. So this length right here is in fact 5. Hands up if you learned how to do this in grade 8. Who am I talking? So there's 3 of you. Okay. This is part, coming up with the fact that this line here is 5 long, is part of the grade 8 curriculum, and I will review it later. But for the time being, we'll just assume that Amanat, Rebecca, and Presley are correct. Spoiler, they are. That is 5 long. Okay, so let's look at the next ratio. I did AF and AB. What are my next 2 corresponding sides in the next larger triangle? Instead of AF, I'm going to look at which side in the bigger triangle? AG, good. And I'm going to do AG over what? AC. Cool. So AG is how long? How long is AG? It is, in fact, 12 long. That's cool. How long is AC, Presley, Amanat, or Rebecca? Have we figured that out already? Sorry? It is 15. How did you get that? You're just, the top is multiplied, so the bottom must be multiplied?
That too, but like, because A to
Okay, you can look at it that way too. Yeah. So yes, this length here is 15, the secret hidden knowledge.
How do you do it at a time? How do you measure?
We'll get there. This is something that these guys were supposed to learn in grade 8, and if you didn't, that's okay. I will review that particular piece of information. I don't know when I feel like it. Not today. Or will it bother you? Should I do that right now? Okay, I'll do it right now. So this is 4 over 5. It's not going to be secret anymore, and that's okay. So we'll do AF to AB, AG to AC. We'll do the last ratio, and then I will show you the secret hidden knowledge. So the last ratio then, AG was this side here. So then on the bigger triangle, we're looking at what side? AH, that's cool. So I've got AH over AD, love that. And the length of AH is 20, I think I counted it out before. So then the length AD is going to be what? Those of you who have the secret hidden knowledge? It is in fact going to be 25. Yes, but we don't understand where it comes from, and so this is also going to be 4 over 5. And so the interesting thing here is that all of these ratios, as they relate to angle A, are what sides? Ratio 2 looks at AF over AB. So from angle A, AF is what side? AF is what side relative to angle A? The adjacent side. And AB is? No, it's not opposite. AB is right here. AB has a name. It's the hypotenuse. Okay? So the way we write down ratio 2 is going to look at the sides that are adjacent, ADJ, divided by the length of the hypotenuse, HYP. And right now you guys are like, why are we doing this? What is going on? That's okay. Just humor me. Walk along. This is like I'm taking you to a path in the woods, and then I'm not telling you where we're going, and there's going to be this beautiful outlook at the end. I think it's beautiful anyway. You guys are probably going to be like, meh, but that's okay. So, okay, aside. Here's my aside. Here's secret hidden knowledge. Okay, so here's the secret hidden knowledge that I'm definitely going to review later, that you were definitely supposed to learn in grade 8. And this isn't just the special people who were in like a special math class somewhere secluded in the building. This is literally all of everyone who's ever taken grade 8 in this province is supposed to learn that the following relationship holds true. For a right angle triangle, where we have, so there's my right angle. I'm going to call this little side here A. I'm going to call this little side here B, little b, and I'm going to call this side here little c. There is a relationship between these side lengths for every right angle triangle. Aminat, what is that relationship? Almost. The side A, if you square it and add it to, not subtract, and add it to B squared, you just happen to get the length of the hypotenuse squared, which is c squared. This is the secret hidden knowledge that Presley used to give us the first length. The first length, and this is called the Pythagorean theorem. Pythagorean theorem. And the Pythagorean theorem relates, and the Pythagorean theorem is only true for right angle triangles. It must be a right angle triangle. Same thing with everything we're doing on the bottom of the page here. These ratios are only true for right angle triangles. Yes, Kyla? I'm actually going to show you an example using this triangle down here. Fine, write down the word theorem there. So actually, and I'll rewrite it up here. So for example, the first side, the one that Presley seemed to pull out of thin air, was the side length AB. So that's the one that we're going to use. So let's redraw this triangle here. This is the triangle A, capital A, capital B, capital F. And just by looking at the grid, we know the lengths of AF and BF. We know that BF is 3 and AF was 4. So the hypotenuse is the length, or is the side rather, opposite AF. And in the Pythagorean theorem, we label side AB as little c. Little c.
Not big.
No, it's little c. L-I-L apostrophe C, little c. Okay? You have to say it that way. Little c. It's not little, there's no t's. Lil. L-I-L apostrophe T. Little c. Okay? And no, and you might think I'm being ridiculous here, but I'm being very intentional. We reserve letters to represent different things in different places. It is not big C. It is defined to be lowercase c. It's just that is just the way it is. Okay? Do not mix up. Oh, he just said A, so it's capital. No, it's not. I very intentionally choose the things that I choose. So how this works is this. If we want to know what the length of the hypotenuse is, we're going to use the Pythagorean theorem, a squared plus b squared equals c squared. Now, a and b, it doesn't matter which side lengths go into little a and little b, but it has to be the two smaller sides. So let's say that little a squared is 3 squared plus, and now I've got little b is 4 squared, and that's going to equal the length of c squared. What is 3 squared? 9. We're using bed mass here. What is 4 squared? So that's going to equal c squared. What is 9 plus 16? So 25 is going to equal c squared. So how do I get c then if c squared is 25? What must I do to both sides? I must square root it. So I square root both sides, and I get that c is equal to? Okay, so that is how we got that the length AB was 5. And Presley looked at that and she said, wait a second, I've seen those numbers before. Because 3, 4, 5 is a special triangle. We call it a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. There's a relationship there. Again, all of this was stuff that was technically supposed to show up in grade 8. And if it didn't, that's okay. Welcome here. The secret hidden knowledge is now yours. Okay, so I'll show you how the other ones work here. I'll just talk it through. Hopefully that's okay. I need you really to be tracking with me here, and if you're not able to track with me, then by all means go back and watch the video later. So then AC we said was 15 long. Gavin used his secret hidden knowledge to come up with 15. So let's use Pythagoras for it. CG we said was 9. AG was 12. So then to find AC, we're just going to do 9 squared plus 12 squared is going to equal C squared. 9 squared is 81. 12 squared is 144. Equals C squared. What's 81 plus 144? 225 equals C squared. So what's the square root of 225? 15. That was one of those perfect squares that I wanted you to remember. Memorize even, back in chapter 1.
So it's always going to be squared.
Sorry? What do you mean?
Like
Yeah, 225 is equal to c squared, yes, then we square root it to get.
No, I mean like the first thing every time you're going to
9 squared plus 12 squared equals c squared, yes.
Will it always be? So it's always
No, I concocted this to work out as being perfect squares. I designed this to work out that way. It won't always be.
So what happens? What do you do in the?
You just use decimals. You just take the square root of whatever and give me the decimal number. For the sake of this example, I picked perfect squares. Okay, so that's how we got 15. So then the last one's the same deal. But I'm not going to show you, but now we can establish that it's 25. Okay? So we've ratio 1, which is the opposite length to the adjacent length. Ratio 2 is the adjacent length to the hypotenuse, there's one relationship we haven't done yet. That's going to be, what do you think? The hypotenuse and the opposite side. And specifically, we're going to do the the opposite side, rather, divided by the hypotenuse, HYP. And why that one instead of hypotenuse over opposite? Because I said so. It's just the way it's going to be. Because there are other we could flip both of these and get other things, but I'm not going to. For the sake of what I want to show you today, it's these three ratios that I'm introducing to you. Yes?
When we get into non-perfect squares, are we just allowed to have two decimal places?
I will tell you what I want at the appointed time and place.
Okay.
I will tell you.
And I had another question, but
We'll do my question first.
okay.
So, in the small triangle here, you know already, I've told you we did opposite and adjacent, we did adjacent and hypotenuse. The only side combination left is opposite and hypotenuse. So in triangle ABF, what side is the opposite side relative to angle A?
Yeah.
It is, in fact, BF. We've already labeled it. Love it. So we have BF, and the hypotenuse is AB. So this is going to equal, what are my ratios there?
3/5.
3/5. So my next ratio is on the next larger triangle is going to be, I want opposite, which is CG, over the hypotenuse, which is AC. And looking at the numbers, we can pull them from what we did before. CG was 9. AC is 15, so it's going to be 9/15. Which is a fraction that reduces to what? 3/5. And then the last one that we're going to do is going to be the opposite side divided by the hypotenuse. Now from angle A, the opposite side here is going to be DH. The hypotenuse is going to be AD. We can use the lengths that we divined before. DH was 15. AD was 25. And so that ratio had better reduce to 3/5. So all of this was relative to the fact that angle A is the same in all three of those triangles. So if the angle is the same, that means the ratios of the sides must be the same in all of those triangles. And you're sitting there being like, whoop-de-friggin' do. Why does any of this matter? And no, don't say that. I assure you it does. The fact that all of these ratios are the same relative to a given angle unlocks this entire world of trigonometry for us. We give these ratios names. This first ratio that said the opposite side divided by the adjacent side, we call that ratio the tangent ratio. Okay. We say that the opposite side divided by the adjacent side is defined to be the tangent ratio. The adjacent side divided by the hypotenuse we call the cosine ratio. And ratio 3, the opposite side divided by the hypotenuse, we give the name the sine ratio, S-I-N-E ratio. And what these ratios allow us to do is these ratios allow us to compare lengths of triangles and angles that we may or may not know within those triangles and find missing pieces of information. So for example, if I know what angle A is and I know what the opposite side is, because I know that these relationships hold true the way they are, I can find either the length of the hypotenuse or the adjacent using this thing called the tangent ratio, or the cosine ratio, or the sine ratio. And this has a whole bunch of really interesting applications. For example, an application of where we're going here is the ancient Greeks who actually established that our world is a sphere. We knew that the world was a sphere thousands of years ago. Anyone who says, oh no, they thought the earth was flat, that was made up by an American textbook sometime in the 1400s. Or, sorry, 1600s. 1700s. Okay? We knew the earth was a sphere thousands of years ago. The Greek astronomers did it. Chinese cartographers did it. We knew. But we can use these ratios to do something called triangulation. Hands up if you've ever heard that fancy word before. To triangulate something. We use that word to things like the global positioning system. Knowing where you are on this planet is just an application of right-angle triangles made with three different satellites and you. If three different satellites have a read on your position, they can triangulate exactly where you are on this globe using this information. This is all this is. So there's a whole bunch of really neat applications of these really simple ratios. GPS doesn't work if trigonometry isn't discovered, for example. So let's flip the page and actually start using this at its most basic level. Here we go. So, in a right-angled triangle, and a right-angled triangle, just so we recall, it has a 90-degree angle. You can use these relationships between the sides and the angle of your choosing to find missing information, which can be really useful. The three primary trig ratios are the sine ratio, the cosine ratio, and the tangent ratio, which we've already given as the sine ratio is the opposite side divided by the hypotenuse. The cosine ratio I gave to you as the adjacent side divided by the hypotenuse. And the tangent ratio, which is given to us as the opposite side divided by the adjacent side. Yes, Danny.
So the Pythagorean theorem is only applied in right angle triangles?
Yes.
Okay, just double checking that.
We also have Pythagorean which is a squared plus b squared equals c squared. When I did that example on the previous page, how many of you recognize it? I'm like, oh yeah, I kind of maybe did that in grade 8.
I've heard it.
Hands up if you are like, yeah, I've seen that thing before.
I've heard it one
Okay,
time.
because that is technically part of the grade 8 curriculum. We're going to use it. If you're uncomfortable with it, I will happily assist you with it. But because I know that the last 2 years of COVID, math has done all sorts of crazy things. You've had shortened time and all that kind of stuff. But we're going to use this. So I use this language here, primary trig ratios, because there are more than just these three trig ratios. It's like we have primary colors, but there are more colors. Well, the other colors are just combinations of these three primary colors.
Right.
Okay? So the other trig ratios are just different combinations of the same pieces of information we have here already. If we wanted to, for example, if you wanted, I'll do it on the side here. The sine ratio we said was opposite over hypotenuse. What if we wanted hypotenuse over opposite? Well, that's not the sine ratio. I gotta make sure I don't screw this up. Because I've only actually used 2 of the 3 before. It is, yes, that's exactly what I want right there. We call that ratio, oh no, where did it go? Hypotenuse over opposite. We call that thing cosecant, which we abbreviate as cosec. If you wanted hypotenuse over the adjacent side, That ratio is called secant, which we abbreviate as sec. And the last one, if you wanted the adjacent over the opposite side, now things got weird here because sine became cosec and cosine became sec. You'd think that sine would be sec and cosine would be cosec, but they're not. They're the opposite.
Okay.
Just, I don't know why.
Order here.
So sine is cosec, cosine is sec, which is weird. Tangent ratio, you saw it was opposite over adjacent. Adjacent over opposite was the opposite of, it's the flipped, right? We flipped this, took this side, we flip it, we got this one. We call that, they're just flipping it.
Oh,
Yeah.
I thought we were combining. Okay,
No,
that
no.
makes more sense.
We're just flipping these ratios.
Okay.
Adjacent over hypotenuse, we call cotan. It does sound like a tropical island. And I assure you a tropical island is better than cotan. Okay, so we've got cosec, we got secant, we got cotan. Using these different sides here. So let's review here. I really do appreciate you guys hanging on as much as you can. I know a lot of this is just in language and me trying to set this thing up. You're probably not going to have homework today because maybe we'll see. We'll see. Because I am purposely going through this a little slowly, and I'm just hoping you're able to hang on. So this triangle here, this little symbol right down there, that cute little guy, that is a Greek letter. We call that Greek letter theta. Okay, and we use theta, like we have variables x, y, z. You've used them before. We jump into the Greek when we are using variables for angles.
Okay.
So this is just a variable for an angle.
It would be cute if it's called theta, not theta.
It's theta. We have some other ones. We've got this guy here. If you don't like theta, maybe you'll like this guy instead. He is drawn as a stick or a circle with a stick vertically through it. That guy's name is phi, P-H-I, which is almost Phil, but it's not, it's phi. Okay, and this is yet another variable for an angle. And we actually only have two. Because these two angles, they cover all of our possible situations. The other one is a 90. We've got a theta, we've got a phi. And the reason I say we only use two because they cover all the possibilities, because theta, believe it or not, here's a crash course for you. If I wanted an angle in this plane and spin this way, all of those angles are what we call them theta angles.
Okay.
If I wanted anything else, so I could go this way, this is theta. This way is all of the phi angles.
Okay, the line's that way.
So it goes a circle that goes up and down. So if I wanted any position in this three-dimensional world, I could go over a little bit theta and up a little bit phi, and I have this position. Or I go over a little bit more theta and down a little bit phi. I can get any position in three-dimensional space using these two variables, which is why we only have these two, these Greek letters theta and phi, because they can give you any position in 3 dimensions with just two angles.
But it really depends what angle you're at.
It actually doesn't, because we define 0 a particular way. So we've got theta and phi. We've got these ratios from this angle now down here. Let's label opposite, adjacent, and hypotenuse. Which one is opposite? Oh, and I screwed this thing up too. That's okay. Which one is going to be opposite theta? Which side is opposite from angle theta? From angle theta, which side is opposite? The up and down one. Yeah. This guy here, from this angle, this guy here is opposite. I'm just going to write it as OPP. Which side is adjacent to angle theta? It's either the sloped one or it's the bottom one.
Wait, what?
The bottom, because the slope is the height.
The sloped one is the hypotenuse because it is across from, and I'm going to do a different color for this on purpose. This one, the sloped one, you want to be real careful. The sloped one in this case is across from the 90, and that one has a name always. We call it the hypotenuse. And so it's never going to be labeled as adjacent, even though, yes, it technically is beside. We don't call it that because it has its own name.
So the bottom one's adjacent.
The bottom one is the adjacent one. What if instead, let's use red, I used this angle up here, phi? Which side would be opposite angle phi? The one that we previously labeled adjacent would now be opposite if I chose a different angle. Which one would become adjacent? The one that was previously labeled opposite. Good. And so this is what Carolyn was asking earlier. What if I had just arbitrarily chosen the other angle instead of the angle that we used? Well, then I would just label opposite and adjacent differently. Everything else will still flow the exact same way. Okay? So you get a little bit of freedom here. How you choose to label things is going to determine how you pick your angle is going to determine how you label your side lengths. Angle picking is the independent variable. Side designation is your dependent variable. To reference what we just did. No, don't write that down. So opposite is across from your chosen angle. The hypotenuse, let's jump down there, is across from the 90-degree angle. And adjacent is the convoluted one. It's beside your chosen angle, but not the hypotenuse. So, as we finish writing all that down, how are you feeling? Tired? There's a lot that went on here. Okay? So I am going to, this is where I'm going to stop. Okay? Because I know I'm seeing a lot of fatigue from some of you, from a lot of you actually. And I know I talked at you a lot. We're going to put all of this into practice tomorrow. But today I just wanted to lay down some of the background here. So thank you for sticking out with me. We're going to give you guys a bit of a break. I'll give you a choice with how we want to spend the rest of class. We can either GeoGuess or we can mind trap. Okay, so let's GeoGuess. Okay.